So here is another case where there is a reactions, but there is an inflow and outflow. This is pretty common for most of the ponds, detention pond. So for instance, if I write here, this is a system, detention pond. Let's write detention. And there is a Q in coming in, and there is a certain amount of contaminants coming in the system. And there is a pollutant concentrations that leaving the system at certain flow rate. And the volume of the pond is V. Let's say the concentration of pollutant in the pond is C. Now we have to calculate what's the effluent concentrations, or what's the concentration of pollutant in the pond. Well, there are certain assumptions you have to make. The very first one is the relationship between the concentration of pollutant in the pond and the concentration of pollutants that leaving the systems. If you think other way, the amount of water that comes out of the system is the same water that is in the systems. If we assume this is a well-mixed system, the pollutant concentration here, C, has to be what's the pollutant concentration that leaving the system, because there is no reactions in the effluents. That's again another assumption. So what assumption we can say is, assumption in most of the cases, we can say that what's the concentration of inside the pond should be the concentration that's coming out of the pond, that's C. If we write that one, then the typical mass balance equations would become P dC over dt, that's the system react concentration, which is C, would be Q in, C in, minus Q out, C out. Again, because we are saying phi out is the same as C, so we can just write as just C. Then reaction terms, volume time the rate constant. So again, if let's say this is first order reaction, so that will be Kc. Because the reaction decrease the concentrations, that's what we are assuming here, we can write negative signs over there. So another, we can also simplify it. We know that the retention pond volume doesn't change over time. It only happens if the amount of water that deliver into the system is the same amount of water we take out of the systems based on the flow rate. If we do that mass balance, then we can say that mass balance for flow rate would be Q in has to be equal to Q out, should be equal to Q. If we write that way, this is again simplified. So we can say this is Q plus C equal to this number. Now the final form, if we write simplified in a linear differential equations, that will be dC over dt. Then if we take all the term that comes out of the system here, plus take C common, so Q plus V K would be equal to, if we divide this V volume terms over all both sides, so that would be V cancels, so we can write this as just this term would be, this time would be Q C in by V. So this is just a rearrangement of volume term from both sides and taking one side into other side. So if you see this form, looks like linear first order differential equations. So that will be dy over dx. If you search in Google what's linear first order equations, that will be px y should be qx. So here x equal to t, y is c, and then px or pt is q over v plus k, and q qt is a form which is basically q c in over v. Let's write a small p, that way it's easier to distinguish between q as a polynomial equations. So this will be small q. That way we can write this one as a small q. That way we don't have any confusion between p, q as a different terms that we assume versus q as a flow rate. So now what we did is we changed that equation into a form that has a very specific solutions. If we say this is linear first order differential equations, and usually that has a solutions. If you see this here, this link, you can see how that equation is derived. But I'm going to write the solution directly here. The solutions of any differential equations, linear first order differential equations, has this form. If we have p over qx, that would be, let's say if I write the generic formula for differential equations, dy over dx plus p y equal to q, then the solution is y would be, or yx would be, the function of x would be e to the power p dx. That's the integral there. This is the integral on the left side. This is integrations. Then q dx plus a integration constant divided by the same exponential p dx. This is the formula. Now we know that y is here c, t would be, we just have to write that equations. To the bottom, e dx is x is t here if you write this side, and p is this term, which is a q over b plus k. And the top one is first integrations, again is the same way, q over v plus k dt, and the q term over here is this q c in over v plus c. If you solve e to the power q by v plus k dt, so that would be e to the power, this is a constant, so that will come outside, so it will be q over v plus k times dt. I'm sorry, this is times t. So if you plug that number over there, then this term become, the bottom would be e to the power q over v plus k t. Actually, if you see, this is yeah, that's correct. This term over here, it will be e to the power q over v plus k t q c in over v plus c. If you write this value, so it will be q v plus k t, and this term on the here would be, this is a constant, this is also a constant, so e to the power at, if you take integration dt, there is a term here dt, So that will be 1 over A. So same way, if you write this one, it will be 1 over Q over V plus K T. I'm sorry, there is no T here. Time e to the power Q over V plus K T Q over V C in plus C. So this is the integration constant that you can solve based on boundary conditions. Again, you don't have to remember these equations. You can write it as a generic formula if you want to calculate what's the concentration of pollutants that change over a period of time. Rarely we need this formula. But if you do need at any times in your career, then you know that this equation exists. But in most cases, we solve for steady state. Steady state means here the very first term over here is 0. Then it changed the formula into a very specific manageable formula. So if you write it here, the left side is 0, then we can write that would be, sorry, this is not cancel. Y is coming here. All right, so let's see, steady state. For steady state, we know that from this equation over here, that will be Q in, the very first term is 0, Q in, C in, minus Q out, C out. Then the reaction term here, that will be K, C, V. That's the first order reactions. And we know that Q in equal to Q out, so that we can write C in, and then we can write Q out is the same as Q, then C out is C, it's minus K, C, V. Then it's very easy to solve for C. Q C in minus, if you take C common, it will be K V is 0. That means C out or C in the pond would be Q C in Q plus KV. Another way we can change that form to C in, divide Q in both sides, this will be 1 plus K volume over flow rate. Well, if you think what is volume over flow rate, it means, it's a term that we all know. This is a residence time, or we can write residence time. It's the amount of time water stays inside the system. That's unique for a system. That means if you have a larger pond, that means the water will stay long period of time. That means there will be more chance for reactions. So this is the way we write is T or tau. So this would be C in 1 plus K tau. So this is the equations that can predict what's the concentration of pollutant in the effluent from a pond when there is system coming in and leaving the systems with reaction terms. Okay.